So, is ethanol soluble in water?
Yeah.
That's very confident. It's a good thing you don't have a car. I'm smiling. I keep forgetting you guys can't see when I'm smiling. I'm smiling most of the time. About 92% of what I say in here is a joke. That was really confident. Can you explain it based on what I've been talking about? Is that how you explained it?
What?
Did you know, is your guess that ethanol is soluble in water based on hydrogen bonding analysis?
It's based on hydrogen bonding and also the, like, I've seen alcohol.
Right. Everybody's seen a bottle of wine, a beer, it's one phase. Anybody a smart ass? So I asked this, this is a pretty common question. I asked it on Thursday, like, is a beer one phase? And I'm just kind of going through the motions. Somebody's like, no, it's got gas in it. Like, yeah, so a beer's got bubbles, the carbonation. But ethanol is freely soluble in water. And again, this is something you draw on your own experience. And you can get this from hydrogen bonding. So this O can hydrogen bond to the H, that H can hydrogen bond to the O. Ethanol, when it inserts itself into the water, can behave very water-like. Okay? So it's soluble. So we come back over here to this molecule that I asked, is this molecule soluble in water? And you guys kind of arrived at, yeah, that probably is. So let me ask you now, is this molecule that I drew earlier in class more or less soluble in water than ethanol?
More.
Got a more? You think more? Why more? So what is hydrogen bonding in this molecule? Where are the well, I guess I'll just, right? That oxygen is just like an ethanol oxygen, it can hydrogen bond. That OH, that's a hydrogen bonder. NH is hydrogen bond, both the N and the H. Nitrile electrons, the nitrogen there, it doesn't hydrogen bond quite as well as that one, but it can still do it. So you got 4 hydrogen bonding places. What would argue against it?
It's like a bigger molecule.
Yeah, it's a big, like there's this big greasy thing here in the middle. This is a benzene ring. Talk more about that later. This part doesn't hydrogen bond at all. The ethyl part, or the 2 carbons in between the N and the O, don't hydrogen bond at all. Right? So judging solubility is a bit of, it's actually really hard to be like, that is soluble, that isn't soluble. And in fact, for most substances, solubility it's not either or. Right? Ethanol is soluble in all proportions with water, and water in ethanol. Ethanol and methanol are soluble in all proportions. Methanol with water in all proportions. This molecule, the organic bit, probably kills that a little bit. But here's the thing. I don't know. I drew that molecule this morning to talk about line structure. So what do? How do you answer that question?
Find out, like mix them together and see.
Right. We don't sit here in class and draw things and argue. We go find the molecule or make the molecule and we put it in water and we see. All right. So a lot of, and this is going to come back to bite me, but a lot of the theoretical side, you can't get close enough without going in the lab. So experiment always trumps theory. You guys all say this should be more soluble than, can't really be more soluble than ethanol. Forgot that's where I was going with it. Ethanol is freely soluble. Okay, so this could be as soluble as ethanol. But, and your explanation is good. Like, I'm not arguing with anybody's explanation, but if you made this and it doesn't dissolve, you're wrong. Now, as soon as I say something like you're wrong, the first time you're in an Orgo 1 class, like everybody gets a little tense. Because I've said I'm going to give you problems to work, and I'm going to judge you on how well they're done. I will know, and also by far, the best thing to do in solubility is not, is this soluble? But is it more or less soluble in something else? It's a comparison. Which of these two molecules boil? So I asked you what the boiling point of hexane is. 15C. It's a perfectly fine guess. Like, what is, you really need a encyclopedia of knowledge to make comparisons. So what I would ask is, a better question would be, even asking ethanol versus hexane is tough. Very different sizes, very different intermolecular forces. But I might ask, right, so there's octane. I might ask you to rank the boiling points of octane and hexane. Right? They both only have van der Waals forces, so the bigger one has a higher boiling point. It's really hard for you to tell me what the boiling point is, but you can tell me this one ought to boil higher than that one. If you have, 4 hydrogen bonds instead of 1, everything else is the same. So if this molecule that I started with had 4 hydrogen bonding spots and was the same size as ethanol, yeah, it'd be more soluble. But it's also bigger and has greasy spots. Greasy stands in for hydrocarbon, right? Like oil. Okay, with just a few minutes left, let's do hybridization. So take a second. How many sp3 carbons, how many sp2 carbons, and how many sp carbons? Feel free to just sit there and stare at me if you have no idea what I'm talking about. All right, so hybridization is sort of an approximation between, just memorizing that carbon has 4 bonds and understanding molecular orbital theory. MO theory is our current best explanation for the way atoms make bonds to one another. It's also really complicated. I shouldn't exaggerate it quite like that, right? It's more complicated than it needs to be for carbon, which is a pretty simple atom. Again, second row, can't go beyond the octet. For a large number of small molecules, hybridization works just fine. And in fact, in learning how carbons behave, using hybridization as an approximation works really well. I'm hedging an awful lot. I will expect you guys to be able to identify the hybridization of atoms and to understand how they interact, how that governs their chemistry. For the handful of you that go on to take PChem or higher level chemistry, I don't want you to be able to look back and say, Dr. Jones lied to you. All right, hybridization is an approximation. And it's an approximation of how the valence orbitals interact. So, right, carbon's 1s2, 2s2, 2b2, 6 electrons. Essentially, when carbon makes bonds, and again, this is a very natural process. This is like water falling downhill. The s and the p the 3 p orbitals mix, just like the atomic orbitals of one atom mix with the atomic orbitals of another to make molecular orbitals. And the 3 ways that can happen, right? So we can get 4sp3 where they just all mix together. you could get 3 sp2 and a p, or you could get 2 sp orbitals and a p and a p. And the important thing here is looking at a structure, the 4 and the 3 and the 2 tell you how to figure this out. So an sp3 carbon will be attached to 4 things. Those things could be either atoms or lone pairs. An sp2 carbon will be attached to 3 things, and an sp to 2 things. All right, the 4 things is simple. That's going to be a carbon that's got 4 single bonds. An sp2 carbon will have 1 double bond. An sp carbon will either have a single bond and a triple bond, or 2 double bonds. So as we look at this, I'm just going to write this. I'll just write it up here now. Because we're running out of time, and I don't want to hold you over. So to identify the hybridization of a carbon, or a nitrogen, or an oxygen, you look at how many double bonds it has. How many pi bonds. We'll talk more about the chemistry of pi bonds next time. But this carbon that's got 2 things attached to it, it's got a nitrogen and a carbon. Only 2 things. One's a triple bond, that's going to be an sp carbon. Sp carbons are going to be linear. All right? It's only got 2 things, they're going to be straight out. Carbon dioxide. 2 double bonds, it's a linear molecule. The carbon of carbon dioxide is sp hybridized. What are the oxygens of carbon dioxide? They're sp2. So, that's a terrible lone pair. This oxygen has got a carbon, a lone pair, and a lone pair. 3 different things, 1 double bond, so it's sp2. The carbons in the ring of this molecule that all have 1 double bond and 3 things. Remember, it's only shown to 2 things. This carbon is bonded to that carbon and that carbon, but there is also an H there. So 1, 2, 3 things are attached to that carbon, it's sp2. So sp are going to be linear. sp2 will be trigonal planar. And sp3 will be tetrahedral. Right? The sp3 atoms here, there's a nitrogen, a carbon, 2 hydrogens that aren't shown, all single bonds. If a carbon only makes single bonds, it's going to be sp3 hybridized tetrahedral. All right, we'll pick it up there. I'm not quite done with chapter 2. This is important for everybody. So the next thing to look at is resonance. Those of you that are in class on Thursday, we'll be doing some resonance structures. In fact, if you want, as a little homework, this molecule we've been working with, not water and ethanol, but this one over here, draw some resonance structures for this molecule. And then we'll do that on Thursday, whatever day it is, and then we'll go into chapter 4. Again, we're skipping chapter 3 for now. We will come back to it. There will be a quiz on everything I've done up to now this weekend. It'll be online, it'll be on Canvas. You'll get to take your pick of when to do it. Who's got lab with me here in just a minute? Doesn't that suck that we have to go write the lab? It's okay for you guys to say that. Like for right now, I'm not. I didn't just say suck on video. I'm sorry.